Welcome to all of you. Now we discuss MCQ 2022 paper CC-4 Modern Algebra University of Calcutta Mathematics Honors. Question paper 2022 question 1a. Let G be a group and A belongs to G. If order of A equal to 17, then order of A to the power 8 is what? Now order of A equal to 17, hence A to the power 17 equal to E. 17 is prime. Let order of A to the power 8 equal to M, then A to the power 8M equal to E. M is the least positive integer. Therefore, 17 is a divisor of 8M. This implies M equal to 17 as M is the least positive integer. Hence, order of A to the power 8 equal to 17. Alternatively, we can apply this formula, order of A to the power T equal to N by GCD of Tn, where N is the order of A. Here, N is 17 and T is 8. So 17, 8, GCD of 17, 8 is 1. So order of A to the power T equal to 17. Correct option is 1. Next question B. Let S naught be a semigroup. Let E and E dash be left and right identities respectively. Then correct option is what? Let A belongs to S be any element, and let E and E dash be left and right identities respectively of the this S naught. Then E naught A equal to A for all A belongs to S, because E is the left identity, and A naught E dash equal to A for all A belongs to S, because E dash is the right identity. Now E naught E dash equal to E dash by the property of E is the left identity. Again, E naught E dash equal to E by the property of right identity. Hence, E naught E dash equal to E dash equal to E. Hence, correct option is 3. Note that if a group wide G naught contains a left identity as well as a right identity, then they are equal and the equal elements is the identity in the group wide. Here correct option is 3. E equal to E dash. Next question C. Consider the group Z2 equal to the set of order pairs AB such that A, B belongs to the set of integers Z under component-wise addition. Then which of the following is a subgroup of Z2? This Z2 means Z cross Z. And this component-wise addition means order pair A comma B plus order pair C comma D equal to A plus C comma B plus D order pair. Let H is the set of all those order pairs AB belongs to Z2 such that 2 divides A and 3 divides B. We choose here this option 4. So 2 divides A and 3 divides B. 2 divides A means that is 2 divides 18, that is 18 equal to twice K. So we write 2 divides 18. So 2 divides A. So A equal to 2K and 3 divides B means B equal to 3K dash. Since 0, 0 belongs to H, then H is a non-empty subset of Z2. Let A B order pair and C D order pair belongs to H be any two elements. Then by the property of H, this 2 divides A, 3 divides B, 2 divides C, and 3 divides D. So we get A equal to 2K, B equal to 3K dash, C equal to 2L, D equal to 3L dash for some K dash, L dash belongs to Z integers. Now order pair A comma B plus order pair C comma D equal to order pair A plus C comma B plus D belongs to H, because A plus C equal to 2K plus 2L, this is equal to 2 common K plus L, this is equal to 2M, where M equal to K plus L. M belongs to Z. And B plus D equal to 3K dash plus 3L dash equal to 3 common K dash plus L dash equal to 3M dash. This M dash equal to K dash plus L dash. This M dash belongs to Z. Thus, 2 divides A plus C and 3 divides B plus C. So, this AB plus CD, so actually H is closed with respect to this addition. Now, order pair AB plus order pair minus A minus B, this equals to A minus A comma B minus B, so this is equal to 0, 0. So minus A minus B is the inverse of AB, and minus A minus B belongs to H because 2 divides minus A and 3 divides minus B. So H is a subgroup of Z2. This theorem, let G naught be a group and non-empty subset H of G forms a subgroup of G naught if and only if A belongs to H, B belongs to H implies A not B inverse belongs to H. Alternatively, we can write A belongs to H, B belongs to H implies A not B belongs to H, closure property, and A belongs to H implies A inverse belongs to H is inverse property. Combinedly, we can write this. So, correct option is 4. Which of the following is subgroup of Z2? Correct option is 4. Now note that for extra this for this set AB belongs to Z2 such that AB belong equal to 0. For this H equal to AB equal to 0. Now 2 0 belongs to H because 2 into 0 equal to 0, and 0 3 belongs to H because 0 into 3 equal to 0. But 2 0 order pair plus 3 0 0 3 order pair equal to 2 plus 0 0 plus 3 is equal to 2 comma 3 does not belongs to H. Hence H is not closed. So this H cannot be a subgroup of this Z2. Next option 2. AB is set AB belongs to Z2 such that A 3A plus 2B equal to 15. For this, this 0 0 does not belongs to H, as 3 into 0 plus 2 into 0 equal to 0 not equal to 15. So this identity element does not belong to H. So this H cannot form a subgroup of Z2. Option 3, this set AB order pair belongs to Z2. 7 divides AB. Let this now let 7 1 belongs to H because this 7 into 1, 7 divides 7 into 1, 7. So 7 comma 1 order pair belongs to H and 1 comma 7 belongs to H. But 7 comma 1 plus 1 comma 7, this addition plus, is equal to 8 comma 8 order pair. This does not belongs to H because 7 does not divides this 64 8 into 8 64. Hence H is not closed. Hence correct option is 4. Next question D. In S5 symmetric group S5, the permutation this 1 2 5 4 into the permutation 2 4 3 into permutation 1 2 is identical with what? Now the given permutation this F, so F equal to this symmetric group S5. So we can write 1 2 5 4. So 1, 2, 3, 4, 5. 1 image 2, 2 image 5, 5 image 4, and 3 to 3, 4 to 1, 4 to 1. For this cycle, this 2, 4, 3. So 1, 2, 3, 4, 5, 2 to 4. So 2 to 4, 4 to 3. So 4 to 3, and 3 to 2, 3 to 2. 1 corresponds 1 and 5 corresponds 5. For this cycle 1, 2, 1, 2, 3, 4, 5. So 1 to 2, 2 to 1, 2 to 1, 3 to 3, 4 to 4, and 5 to 5. Now, this alpha, beta, gamma, say this permutation alpha, this permutation beta, this permutation gamma, then we get this, and starting from this right end, 1 image 2, 2 image 4, and 4 image 1, so 1 image 1. So we can write this scheme under gamma is 1 to 2, this gamma is 2 to 4 for beta and 4 to 1 for alpha. So 1 to 1 for this product. And similarly for others, 2 to 1, 1 to 1, and 1 to 2. So 2 to 2. 3 to 3, 3 to 2, 2 to 5. So 3 to 5. So we get 3 to 5, 5 to 4, and 4 to 3. So we get these 3, 4, 5, and cycle of length 3. So correct option is 3. Next question E. Let Z not be a group with x not y equal to x plus y plus 2, x comma y belongs to Z, then the inverse of x is what? Let E be the identity element of this group. Then E not x equal to x for all x belongs to Z. So by this definition, E not x equals to E plus x plus 2 because x not y equal to x plus y plus 2. So E plus x plus 2 equal to x. So equal to 2 by cancellation properties. So E is the identity element is 2 minus 2. Let x dash be the inverse of x in this group. Then x not x dash equal to E. E means minus 2. And x not x dash means x plus x dash plus 2 is equal to minus 2. So x dash equal to minus x minus 4, that is minus common x plus 4. So inverse of x is minus common x plus 4 bracket. So correct option is 1. Next question F. Which of the following is true? Zn is cyclic if and only if n is prime. Every proper subgroup of Zn is cyclic. Every proper subgroup of S4 is cyclic. Every proper subgroup of a group is cyclic, then the group is cyclic. Correct option is 2. Every proper subgroup of a Zn is cyclic. Now we know this Zn is the set of residue classes modulo n. So this class 0, class 1 to class n minus 1. And this Zn with addition modulo forms a group. This group Zn, this plus addition modulo n, is a finite group of order n. Now class 1 belongs to Zn. So order of class 1 is equal to n, is the class 1 is equal to n. So Zn plus, this is a cyclic group for all n belongs to n, capital natural number. The composition plus is the addition modulo n. Class 1 is the generator of Zn. So we can generate any elements with this adding class 1. So class 2 equal to class 1 plus class 1. class 3 equal to class 1 plus class 1 plus class 1 3 times adding. So this class 1 is the generator of Zn. Theorem: every subgroup of a cyclic group is cyclic. Hence, every proper subgroup Zn is cyclic. Hence, correct option is 2. Every proper subgroup of Zn is cyclic. Next, Zn is cyclic if and only n is cyclic. N is prime. Note 1. Zn plus is cyclic for all n belongs to n. So option 1 is false. This Zn is cyclic if and only if n is prime, but if n is not prime, then also Zn is cyclic. So this option is false. Next, option 3. Every proper subgroup of S4 is cyclic. Now, Sn is the symmetric group of degree n with respect to multiplication of permutations on the set S equal to the set 1, 2, 3, 4 up to n. Sn is a non-commutative group for n greater than or equal to 3. Every cyclic group is commutative. That is, every non-commutative group is non-cyclic. Hence, S4 is non-cyclic. Now, consider a subgroup V from S4. This equal to the sets E, identity permutation. This cycle 1, 2 into 3, 4, comma, 1, 3 into 2, 4, 1, 4 into 2, 3 of the group S4. And the order of H equal to, sorry, this is the V, actually, not H. The order of V. Order of V is the 4. Now, this 1, 2 into 3, 4. Actually, this is the 1 image 2, 2 image 1, 3 image 4, 4 image 3. This order of this permutation is 2. Order of this permutation is 2 also. And order of this permutation is 2 also. And this is the identity permutation. Order of identity permutation is 1. So, this V is the Kleins 4 group. And it is an abelian group of order 4. There exists no element of order 4 in V. Hence, this subgroup V is not cyclic subgroup of S4. So, option 3 is false. Every proper subgroup of S4 is cyclic. No. Here, we consider this example. This Kleins 4 group from S4 is not cyclic. This is a proper subgroup of this S4, but not cyclic. And option 4. Every proper subgroup of a group is cyclic, then the group is cyclic. No, it is also wrong, because consider the Kleins 4 group V. This is the set E, A, B, C, where A square equal to E, B square equal to E, C square equal to E. Every element, order of every element is 2 except identity. The proper subgroup are B1 is the set singleton set E generated by E, cyclic subgroup. B2, the set E A is generated by A, cyclic subgroup generated by A. B3, cyclic subgroup generated by B. B4, cyclic subgroup generated by C. All proper subgroups of V are cyclic subgroups, but V is non-cyclic. Order of V equal to 4, but there is no element in V whose order is 4. V is a subgroup of V itself, and this subgroup V is improper subgroup of V. And E, singleton set E, is the subgroup of V, and this is known as trivial subgroup. This identity element, this is trivial subgroup. Hence, the option 4 is also false. So, correct option is 2. Correct option is 2. Next question, G is the incorrect statement. 1. Every homomorphic image of a group G is a quotient group G by H for some choice of normal subgroup H of G. 2. Any two infinite groups are isomorphic. 3. Z by 4Z is isomorphic to Z4. 4. Every proper subgroup of S3 is cyclic. Now, correct option is any two infinite groups of isomorphic. Incorrect statement. This is the incorrect statement. Any two infinite groups are isomorphic. This is incorrect because these Z plus and Q plus are infinite groups. Z plus is cyclic, but Q plus set of rational numbers, set of integers is not cyclic. Q is the set of rational numbers, Z is the set of integers, or Q plus is not cyclic. The isomorphic image of a cyclic group must be cyclic. Therefore, Z plus and Q plus are not isomorphic. Hence, option 2 is incorrect statement. It's an incorrect statement. Now, note 1. Every homomorphic image of a group G is a quotient group G by H for some choice of normal subgroup H of G is correct statement because from the first isomorphism theorem, we find that if a group G1 is a homomorphic image of a group G, then the group G1 is nothing but G by kernel F. Now, if H is any normal subgroup of a group G, then the mapping F maps G to G by H defined by Fa equal to AH is an epimorphism with kernel F equal to H, which is called natural homomorphism or the canonical homomorphism of G onto G by H. Hence, all the homomorphic images of a group G are the groups G by H where H is a normal subgroup of G. Conversely, every normal subgroup H of a group G is the kernel of some homomorphism, namely the natural homomorphism. So option 1 is correct. Now option 3, Z by 4Z is isomorphic to Z4. This is correct. Option this theorem for 2 is incorrect. Two infinite cyclic subgroups are isomorphic. So option 2 is wrong. Option 3, if G is a finite cyclic group of order n, then G is isomorphic to Z by nz, n belongs to natural number, and this is isomorphic to Zn. So option 3 is also correct. Option 4, every proper subgroup of S3 is cyclic. Option 4, every proper cyclic subgroup is cyclic. Every proper subgroup of a symmetric group S3, symmetric group S3 is cyclic. Now, symmetric group S3 contains these elements rho 0, rho 1, rho 2, rho 3, rho 4, rho 5. And this rho 0 is this 1, 2, 3, 1, 2, 3. Rho 1 is this 1, 2, 3, 2, 3, 1. And by this cycle, 1, 2, 3, 2, 3, 1. Rho 2, 3, 1, 2. These images of this. Rho 3 is the 1, 1, 3, 2. 1, 3, 2 clockwise. Rho 4 is the 3, 2, 1. Rho 5 is the 2, 1, 3. So 6 permutations on the set S. And rho 1 square equal rho 2, rho 3, 1, rho 1 cube equal to rho 0, rho 2 square equal to rho 1, rho 2 cube equal to rho 0, rho 3 square equal to rho 0, rho 4 square equal to rho 0, and rho 5 square equal to rho 0, and rho 0 is the identity element. Now, consider these subgroups. This H1 generated by cyclic subgroup generated by rho 0, H2 cyclic subgroup generated by rho 3, H3 cyclic subgroup generated by rho 4, H4 cyclic subgroup generated by rho 5, H5 cyclic subgroup generated by rho 1 and also rho 2. So all proper subgroups of symmetric group S3 are cyclic. Hence option 4 is also correct. Only option 2, two infinite groups are isomorphic, not two infinite cyclic groups are isomorphic. So, yeah, incorrect option is 2. Is the incorrect option. Next, question H. The number of group homomorphism from the cyclic group Z6 plus to Z4 plus is what? Next question. The number of group homomorphism if maps from Zn to Zm, Zn to Zm, m and n are natural numbers. If x equals to ax is d equal to GCD of mn, where a equal to m by d into k, where k equal to 0, 1, 2, dot, 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 d minus 1. So here Z6 is n equal to 6 and m equal to 4. So d is the GCD of 6 and 4 is 2. So f maps from Z6 to Z4, that is here, so a equal to 4 by 2, actually 4 by 2, m by d into k. M by m is 4, d is GCD is 2, so 2k, and k equal to 0 and 1. K equal to 0 and 1, so a equal to 2k. When k equal to 0, a is 0. When k equal to 1, a equal to 2k. So we get this a equal to 2, a equal to 2, k equal to 1, a equal to 2. So we get this ax, fx equal to ax. So this fx equals to 0 for all x belongs to Z6, and fx equals to 2x for all x belongs to Z6. So we get two group homomorphism for this case. So a correct answer option is 3. Correct option is 3. Two group homomorphism here. Next, question I. F maps 4Z to Z3 is defined by F4n equal to box n. N belongs to the set of natural integers Z. Then kernel F is, correct answer is this. Correct answer what? Now, cardinal F, actually cardinal F is the 4n belongs to 4Z. This is the domain set 4Z. 4n types elements this here, where maps such that F4n is the identity element this in Z3. This is the class 0. Actually, this is the class 0. Class 0 in Z3. So this set 4n belongs to 4Z such that this class n equal to class 0, because F4n equal to class n. So class n equal to class 0 in Z3. So Z3, so class 0 is the multiple of 3. So n is a multiple of 3. That is n equal to 3k. So this 4Z, so 4 into 3k, actually 12k. So this is the set 12Z. So this is the 12Z. This the cardinal of f is 12Z. Correct option is 3. Next question J. Consider the group Q star dot the multiplicative group of all non-zero rational numbers and its group Q plus the set of all positive rational numbers. Then this uh, index of Q plus in Q star is what? Actually, correct answer is 2. Option 1. Because there are two left cosets of Q plus in Q star, and they are Q plus and Q minus, positive rationals and negative rationals. The index of Q plus in Q star, that is this index of Q plus in Q star, equal to 2. Number of left cosets or right cosets. The number of distinct left or right cosets of Q star in Q plus or in Q star. Here note that this Q plus union Q minus equal to Q star. Q star is the non-zero rational numbers, and Q plus intersection Q minus equals to pi null set. Forms a partition. This Q plus and Q minus forms a partition. This. So correct option is here 1. There are two left coset or right cosets for Q plus in Q star. Thank you for watching this video.